Question one, we already know the stochastic process xt is real and is real and WSS. So we can find, so its autocorrelation function is about tau. So we can get R tau is equal to E xt plus tau and xt. So this is the mean. So this is the mean of R of xt, and we can easily to see that this function must be real since xt is real. So this is very easy to get. And for R minus tau, we can get that it's about function t1. Tau is equal to t minus t2. So now it means that t1 is smaller than t2. So we can get that it is a form of this. So we can see that these two parts are the same. So we can get that R tau equal to R minus tau. So we can easily to get that Rx tau is real and even. And for SXX for the spectral for the spectral function, we can get that it's equal to Rx is a Fourier transform of the autocorrelation. And since this part is real, so we can get that Sxw is equal to Sx minus W. Since we change W here, let me show you that if we change it to minus omega, now we can so it's very easy to transfer it into this form. And here is 2 minus infinity. And if we change the symbol of this function, and then we can transfer it to since this is even, so it just can be transferred to this. So this is very easy to get. So we can get that Sx is even. And for here we need to introduce that Yt. We need to introduce a system H omega. We use xt as its input and yt as its output. So the power of this output, we can get that it's equal to and here we can say it depends on the H omega. H omega is what we can define. If we define it as ideal bandpass function, here is B, here is A. So it can be transferred to this form. Here is 1. So it's from B to A. Here, this BA, we can define any value. So for any BA, the power of Y, this output must be bigger or equal to 0 for any B and A. So we can know that Sxw must be bigger than 0 for every omega. Since for any B, any A is satisfied, so we need to satisfy this for any omega. So we can get that Sx x omega is non-negative. Okay, let's move to question 2. Here it gives us 3 functions, and we need to judge that which one can represent if it is a correlation function or the spectral density function that can represent an articulation function of WSS stochastic process. So firstly, we need to know what this question needs us to do. We need to, if we know A, we can infer to B. So it means that A is a sufficient condition for B. So this is sufficient. And this, if we know A, we can infer to B. A is sufficient to B, and B is necessary for A. So here we need to find the B, since it may represent, not must represent. So we need to find the B, and we can infer A. So it means that if we already know it's WSS, then we can infer to B. So for the first question, for the first part, if it is autocorrelation, we can know that it's this, the autocorrelation function, and we can find that if this is the autocorrelation function, it must satisfy that E minus 0 bigger than every for other bigger or equal to. This is very easy to get. And the other situation is that it's even. If it's even, and the last question, situation is that it's SXX. Its spectral this spectral function must be bigger than 0. And for this situation A, we can easily to see that these 2 parties we can get. And if we use Fourier transfer here, and we can get its Fourier transfer is this. So this is S omega. We can say that it's bigger than 0. It's bigger than 0. Okay, let's move forward. Let's see. Let's see question B. And here we can see that is this okay, I forget the spectral function, and we know if it's satisfied, if this is spectral, if we know xt is WSS, we can know its spectral function density function must be bigger than 0, and here we know its spectral function always bigger than 0, so it may represent, not must represent, it may represent. For B, we also can see that it's bigger than 0. This part is always bigger than 0. No. Tau. When it's approaching to 0, and when it's approaching to this function is equal to 1, so we can easily get that this part is always bigger or equal to than this part. So we can get that. Also, we can find its spectral density function is always bigger than 0. So if we have these two situations, these two conditions, so we can think that it may represent. Also, for the next part, If we can say this part is always bigger than 0 if it's a spectral density function, so it may represent an autocorrelation function. Okay, let's move to 3. About 3, we can just calculate its spectral density function, which is we can calculate its spectral density function is this, and we can easily see that this part is not always bigger than 0, so it means it's not non-negative. So we can know that this part, we can know that this, if we cannot represent an autocorrelation function of WS, but it's always bigger than 0. So if it is a spectral density function, it can represent and WS is stochastic process. Okay, that's all.